Hello everyone! In this tutorial we'll be discussing the principles associated with use of pick-and-place techniques applied to specific tasks. A key step in pick-and-place approaches is the identification and recon of the environment. Several techniques can be applied for environment recon. In this tutorial we'll be discussing the RGBD technique. Our approach started by using depth information to detect key objects and structures in a given environment or scene. Given that the robot is located on top of the table and so are the objects of interest, it was necessary to define the table plane on the acquired image. Once the table plane is known, this information is subtracted from the original image, which gives figure depth objects. Then the background image is generated and subtracted from the acquired image, resulting in the figure final depth. This concludes image processing using depth information and allows one to identify all objects in a given scene, as well as their coordinates. Subsequent to obtaining depth information, the image depth referential is converted to RGB referential. The next step is to use RGB information to obtain data on the object's color. Given that we had previously compiled all HSV libraries, it was easier to use HSV color scheme instead of RGB color scheme. Thus, we converted from RGB to HSV. Using the bounding boxes determined using depth information techniques, as previously described, and post-referential exchange from depth to RGB, we focus our image analysis only on those image segments of interest. Subsequently, we double-checked that the identifying bounding boxes contain the objects of interest by evaluating the characteristics of those image segments using the OpenCV library tools. At last, we apply color filters to the image segments identified in order to remove objects whose colors were off specification. For example, the orange was filtered off as this is the color of the robot, rather than the target objects. Once this process was completed, all we had to do was to convert the data's referential from RGB to. There might be cases where the object of interest is hidden behind the robot. When this happens, there are two possible solutions. We can move the robot and reacquire the image, or we can focus the robot camera on the field of view expected to be obscured by the presence of the robot. The second solution is especially suitable for cases where the robot cannot be moved. Once the object coordinates are known and are expressed on the robot referential, we can determine the robot joints by inverse kinematics. This will prompt the robot to move to the object position. To minimize object picking errors, we have added an extra step to the path where the robot stops a half a meter from the object and adjusts the positioning of object picking by acquiring several images from the robot's camera. Those acquired images are processed and analyzed continuously, forming a controlled loop that guides object picking. As the robot adjusts for picking the object of interest, it continuously drops from half a meter to the height of the object. Then, the robot starts the process of grabbing the object, which is accomplished by using a strength sensor that detects when the object is secured by the robot gripper. The secured object is then moved to the target position and is placed using the same principle applied to the object picking strategy. There might be instances where the robot's allocated task requires the picking or placing of the target objects outside of the robot's reaching range. When this is the case, the use of mobile robots is suitable, but requires an additional positioning control, which is beyond this tutorial goal. The described pick-and-place process is repeated for each single object of interest. Thank you for watching our tutorial on pick-and-place techniques.